Hello students, welcome to this session. In this session, we will discuss how we can convert the transfer function to the state space model. So let's take first example. So in this example, the transfer function of the system is given to us. As we already know, the transfer function is defined as the ratio of Laplace of output and Laplace of input, considering initial conditions as 0. So for this particular system, the transfer function is given to us as ys upon us is equal to 1 upon s square plus 2s plus 5. So in this, the output of the system is ys in frequency domain, or in time domain it will be yt, whereas the input of the system is us in frequency domain and ut in time domain. Now the overall objective is to find out these two equations. So if we expand our transfer function, we will get this equation. That means the ys will be multiplied by to the denominator and us will be multiplied to the numerator. Now, if we take the inverse Laplace transform, we already know the transfer function is given to us. That means the initial conditions are already 0. So if we take the inverse Laplace transform, we will get the double differentiation of y with respect to t plus 2 times dy by dt plus 5y is equal to ut. Now this equation is in time domain. Then we know that the order of the equation is 2, so there will be two state variable. So ultimately, how many equations we have to find out? We have to find out three equations to represent the complete state space model. Two equations for the state variable that will actually correlate the differentiation of a state variable with the other parameters, and one equation for the output. So now this particular equation can be represented as y double dot plus 2y dot plus 5y is equal to u, where y double dot is actually nothing but the double differentiation of y with respect to t, and y dot is the single differentiation of y with respect to t. Now we can have two state variables. So let's say the first state variable is x1 and the other state variable is x2. So let's say y is equal to x1 and y dot is equal to x2, and y double dot will be equal to x2 dot. So likewise we can correlate all these state variables with the differentiation of output. Now what we have to do, we have to just replace all those values in our given equation. So if we replace the y double dot with x2 dot plus 2 times y dot will be replaced by x2 and y will be replaced by x1, so it will be 5x1 is equal to u. Now in order to find out the state space model, as we already know, we have to get the differentiation equation for the state variable. So first state variable is x1, so we have to get the equation for x1 dot. The other state variable is x2, so we have to get the equation for x2 dot, and the third equation should be for the y. So by rearranging all these equations, we will get these three equations that are actually for the x1 dot, x2 dot and y. That is what we needed. Now we have to just convert all these three equations into the matrix representation. So we have a two state variables. So matrix A will represent a 2 by 2 matrix. So like this, we can represent our state space model, the input equation. And the second equation will be y is equal to 1, 0 matrix multiplied by x1, x2. And the D matrix is 0. Now we can convert this particular state space model into a block diagram also. So there are two state variables. So two integrators will be there. The input to the first integration will be x2 dot. The input to the second integration block will be x1 dot. And x1 dot is actually equal to x2. So that's why those are connected directly. Now for the second equation, we have to get x2 dot is equal to minus 5x1 minus 2 times of x2. So this x2 is multiplied by 2 given back to the summing block with negative sign, and then the x1 is multiplied by 5 and given back to the summing point with negative sign, and input u will be multiplied by 1 and given to the summing point, and output y will be equal to 1 multiplied by x1, that is our output. So likewise we can represent this particular transfer function into a block diagram representation, and also we have estimated the state space model for this particular example. Now we will take the one more example. So in this example we have the numerator as well as the denominator. In previous example there was only denominator, the numerator was unity 1. So we will proceed. So there is no missing term in the numerator or denominator. If there is any missing term, then we should add that particular term with 0 coefficient. So let's say if s square term is not there in the denominator, or maybe in the numerator, let's say s term is not there. So we can add that term with the coefficient having 0 and complete the particular numerator or denominator equation, making sure that there is no missing term. Then both the numerators and denominator should be in decreasing order. That means the first term is s cube, the second term should be s square, the third term should be s to the power 1, and the last term should be constant. Same as in numerator, if the first term is s square, the second term should be s to the power 1 and the third term should be s to the power 0. And let's say if it is not like that, we should arrange all those terms in decreasing order of power of s. Now we will multiply numerator as well as denominator with a dummy variable qs. So from the first part we will get ys upon qs as a numerator, and the second part as qs upon us as a 1 upon denominator. Now we will expand both the equations. We will take the inverse Laplace transform for both the equations, and then we will start from the last of the equation, and we will consider each term as a state variable. So first state variable will be x1, that is equal to q. The second state variable is x2, that will be equal to q dot or maybe x1 dot. The third state variable will be x3, and that will be equal to x2 dot or x1 double dot or q double dot. Likewise, the third term q triple dot will be equal to q3 dot. So likewise, we will consider all the state variable. Now we have the state variables with us. Now we know there are 3 state variables. So we have to find 3 equations with the derivative of state variables, that is x1 dot, x2 dot and x3 dot, and one output equation. So we will proceed further. We will put all those variables in this particular equation. So we will get from the first equation, we will get y is equal to x3 plus 5x2 plus 1x1. And from the second equation, that is for the input, we will get input u is equal to x3 dot plus 4 times x3 plus 3 times x2 plus x1. Now, using these equations, we can simply estimate our all the state variable differential equations. So these last 2 equations we already find, and the first 2 equations, that is for the x1 dot and x2 dot, that we already assumed. So now we have our all the 4 equations with us. Now what we have to do, we have to just convert all these equations into the matrix multiplication. So there are 3 state variables, so we will get a matrix A with a dimension of 3 by 3. So like this we can represent it as a state space model, the input and the output equation. So thank you for your attention. Likewise, you can take further examples and convert all those transfer functions into the state space model. Thank you for your attention.